So this is just some work that we've been working on with a number of collaborators, some directly contributing to the work with actual code writing and design, and others just through conversations. But it was really motivated by looking at the increasing complexity of next generation storage systems and I/O environments. Couple of things to point out here for storage systems moving forward is that the hierarchy is actually increasing significantly. Oh, am I getting? Yep, okay. The hierarchy is actually increasing significantly in storage systems. We have multiple levels of cache, as well as moving towards things like phase change memory, flash, hard disk drives, and in the supercomputing or HPC environment, we're starting to add these at different levels of the system architecture. Be they in gateway nodes from the large-scale compute platform, or in VRAM directly within the compute platform itself, and different types of caching and with different performance characteristics. And so there's a lot of work going on middleware and other layers to help manage those distributed resources to give a consistent view of the storage hierarchy. But we were interested in looking at it from the Legion model, particularly because we have this strong data model that we can use the runtime to reason about placement of data throughout the system and managing that explicitly without necessarily having the user involved. Also, we're seeing a movement towards asynchronous I/O mechanisms, allowing us to overlap computation with communication, as well as the ability to support different types of producer-consumer workflows with lightweight transactions in distributed storage environments. So all this is cool stuff, but it's getting more and more complex. So what we're looking at with Legion is the ability to manage much of this directly. So we've worked with Ji Hao and Noah Watkins in particular on some work to allow us to map a high-level data structure, distributed data structure. I'm showing a Voronoi tessellation here, but you can imagine a structured grid and actually mapping that to individual shards in a storage system and then maintaining a consistent view of that through the runtime without the application having to specifically codify it. And here's an example of that. It allows us to actually overlap computational phases with the I/O phases in the application. And so there's a lot of talk in the storage systems research community to allow us to have distributed transactions and allow us to have asynchronous I/O mechanisms, but there's a pretty significant gap at the application level on actually how to use this. So we've demonstrated this. We did an initial Legion support for persisting logical regions to HDF5 files. And Ji Hao and Noah, as I said before, were instrumental in this work. We wrote a fairly simple AMR data structure to show that we could actually map different elements in a multi-resolution AMR decomposition to different storage hierarchies with that data structure, allowing us to use colorings essentially to describe those layouts. I have to think a little bit about how we'll use dependent partitioning moving forward, but it should work fairly straightforwardly. And we actually are able to maintain this consistent view of the data structure as it's being persisted independently to different storage elements. Here's a picture of this where we actually did some work looking at this AMR data structure and how we could actually map it different elements of one or more logical regions to different elements in the storage hierarchy. So be it in VRAM or actual disk. And we can then persist in some of these experiments, these performance plots I'm showing, we're actually persisting a static structured grid, not an AMR grid, but the concepts still apply, to multiple independent storage targets concurrently. And we maintain this consistent view, but we're able to get more parallelism out of the underlying storage system without the application having to know about it. And here's an example of our Legion benchmark versus an IOR, which is a pretty common parallel I/O benchmark. And you'll see that we're actually able to scale up to about the peak performance of this storage system given that node count. At 16 nodes, we're at 3 gigabytes per second versus half a gigabyte per second if we do the traditional POSIX I/O interface to maintain a consistent view. We're also able to do asynchronous I/O scheduling, essentially concurrently scheduling both write tasks as well as read tasks based strictly on data dependencies that the runtime is able to actually manage. And we're able to use alternative storage environments such as Rados, which is a fairly well-known or well-used object storage-based system underlying the Ceph file system, and get pretty reasonable performance scalability on that alternative object storage, but still maintaining the same logical view of the data within the runtime environment. And now we're moving on to co-design of Legion and storage system I/O using Pennant. So some of this work is in collaboration with Intel through Fast Forward 2 project. And we decided to use Pennant because it actually has a fairly interesting data model. It's an unstructured finite element code, pretty common in hydrodynamic type applications. It's actually a mini app. And it maps, what we're looking at is mapping the mesh entities to a high-level data model using HDF5 and a virtual data set concept. And this is using a number of new mechanisms that are developed within the Intel Fast Forward project. We're looking at being able to actually overlap computation and I/O, particularly given the type of method we're using within Pennant. And I give an example of that here. And we're going to be exploring some query and subsetting of mesh entities within the storage environment using attributes of the logical regions. So give me every zone that has total energy greater than X 4 times Ti through Tj. We're actually looking at a couple of different technologies to do that in the storage system, but having this strong data model that the storage system can actually reason about is enabling it. And then we're also looking at another use case. It's kind of a producer-consumer use case where we can actually use distributed storage transactions to coordinate repartitioning of the Pennant mesh using kind of an asynchronous method. Instead of just stopping the application and then doing the full repartitioning and restarting the application, or stopping the computation, I should say, in the application, we can actually run the Parmetis repartitioning on a subset of nodes concurrent with the actual application. We'll get a little ahead of it, but based on the physics, the repartitioning should still be valid from a load balancing standpoint. And that's it, other than I have a few more slides that I'll leave in here for folks to review later if you're interested. But I'm actually in the process of SPIMDizing Pennant within Legion directly. And it's a very similar model as was described previously. It's a bit verbose. The C++ API is a little bit verbose in doing so. But once you get past, once you've actually worked through the algorithm in your head in its totality, all of the mechanisms are in place within Legion to support this, this type of workload. One difference is I'm actually using a pairwise coloring of masters of ghost points. And I believe this will allow me to do a little bit of additional parallelism in this unstructured mini app. But if you have questions, just come find me at the break. Thanks. No?
Somebody took the dongle. Did you?
Where's the?
Okay. By the way, did you? Was your mic on?
Testing. Yes.
Okay.
I think we're good. That's mine. You can set this one over here.
All right. Hopefully you can hear me. My name is Stephen Dalton. I work with Mike and Sean at NVIDIA, researcher. Ooh. So I'll say a little bit about what I've done. So I've been a hardcore Legion developer for all of 6 weeks now. So my focus has been mostly on both the software side. Let me start my personal timer here. My focus has been on both the software abstraction side, so how do I talk about these Legion arrays? How do I talk about unstructured graphs? How do I talk about these different execution launch strategies that are going on in Legion, from tasks to index spaces to must epoch launchers? So trying to build up abstractions in order to allow programs to be more productive without actually having to be as verbose as the low-level runtime API. But also, I am not a software engineer by trade. I'm a numerical person, so the things I've done and the things I'm interested in so far have been both structured and unstructured AMG and geometric multigrid methods, some graph partitioning work, parallelizing metas, solvers, and different solvers, and eigenvalue solvers, Krylov solvers. So in the 6 weeks' time, I actually was able to accomplish about 90% of those algorithm goals. It took me, I think, a week to write my AMG solver in Legion, and I'm just going to talk somewhat about how I went about getting things done and the strategies. So about 6 weeks, about a week and a half or so, when you first come to it, for those that are trying to get initiated into this group, when you first run into the hello world example, there's a certain amount of vocabulary that I think you need in order to even interact with these kind of things. What is a logical region, physical regions, index spaces? I work with Mike, so I'll walk down like, what are we talking about here? There is no foothold in the C++, STL style or the MPI world that I could use in order to make analogies with this. And so it was really like I was a deer in the headlights. I was really lost, wasn't really sure what was going on. It really was the case where I felt incapacitated, where I couldn't jump in and just start hacking away, which was my usual tried and true strategy for learning something new, is to just jump in and start breaking stuff. And I was also hindered as well. I was looking for footholds, and so I kept bringing questions to Sean and Mike about how do I write basically MPI applications in Legion. And if you come to it with that mindset, it's pretty much like, I think, learning any foreign language. If you keep trying to speak English and you're trying to learn Chinese, that's probably not going to be as effective as if you try to embrace the new language more completely. And so I would recommend probably not trying to bring other things with you. And so after about a week and a half going over videos, looking at reading the papers and going through all the examples, I was able to actually start hacking. And so I spent a week hacking, and so it went from just being lost to just a day's confusion, wandering around source code, looking at errors, trying to figure out how to debug things. So I started with the CG solver example, found the Legion very verbose, and I just really wanted to focus on one particular thing. And at this particular time, I was really focusing on maximum dependent set algorithms. And so I said, hey, I'll just try to do something with that. And I worked on that for about a week, learning how to spot errors pretty much in Legion and fixing these simple bugs that you inevitably will encounter when you're using the API wrong. But then after that, I reached another area in the plateau, and I reached it pretty quickly where it was revelation. All of a sudden, I was like, this is actually pretty easy. Started writing my own distributed solver API interface. I saw my productivity improving quite substantially week after week. From the first week, I was asking Mike what an index space is. 2 weeks later, I'm asking him, how do I use these epoch launchers and SPMD tasks? And so it ramped up pretty quickly after I got basically the vocabulary and I let go of the previous things that I tried to bring with me. And so new Star Wars movie is coming out pretty soon. So one of the things that Mike actually told me, this is supposed to be Master Yoda in my Vim. But one of the things Mike told me was to start looking at source code more, grepping through the source code in order to find answers to some of my questions. And so my whole strategy after that was to basically just keep legion.h open in a separate window. And I basically, it's I think 5,000 to 7,000 lines, and I've pretty much almost been through all of them. It was just amazing how much they actually did in order to provide some documentation so that you can go through and at least read what these data structures are and how to use certain particular features of the API. And so I really found that to be the most helpful information once I want to get started. And so just to generally talk about my implementation cycle, I was actually surprised earlier. I think Elliot said most people maybe start off with the index launcher in order to make sure they're executing parallel. I didn't start off with any of that. When I first started implementing all of my solvers or my AMG code and everything like that, everything was a task launcher. And this is the simplest thing in order to get started with. Just make everything a task launcher. Learn the Legion vocabulary before you start hacking on anything, even an index launcher. Just the least amount of errors you can have is if you execute everything sequentially, which Legion allows you to more or less express yourself in these sequential form of thinking about your problem decomposition. And so I made everything task launchers, went through, learned the vocabulary. Everything was pretty easy. Then I went to migrated up to index launchers, partitioned up my data, added my CSR matrix data structures, colored them, learned all this stuff about the partitioning API, which with the task launchers, you don't really have to, that's a whole nother bag of things that you have to deal with once you really start to get into it, is partitioning up your data and everything. So starting out with the least amount and then adding on to it, I felt was a lot easier for me to understand. And then about a couple of days after that, I quickly realized that probably wasn't going to be enough. And I went straight into epoch launchers, which was a whole entire set of problems that was on top of it. The fine-grained epoch launchers, and then learning about phase barriers, dynamic collectives, the must parallelism strategy that Legion was doing. One of the things I really liked about the way that I could talk about the problem decomposition was it allowed me to move back and forth between when I was doing from this task to this index. Going from index to SPMD was actually pretty straightforward except for learning about barriers. But I didn't do all of the pieces, say for my multi-grid hierarchy, I didn't do all the pieces at once. I would go through and do one operation and I would decompose it into the index launcher and the rest were in task launchers. And Legion allowed me to actually go through with this partitioned matrix data structure that I had, but I could still, in the next call, think about it as a single task launch, and behind the scenes, Legion would allow me to think about it as a single task launch with all of my data in a single place, perform all those copies, and so I was just progressively adding on another degree of complexity to my code automatically without having to really think about how do I gather this data and execute this sequential code. I just, oh, this one is a task launcher, and I'll just parallelize this one next, and so I was really just chopping off the bits that were simple one at a time. One of the things that was touched on by one of the users, though, was that as you move from this nice, neat world of task launchers where you're doing everything, you're trying to simplify your code, off into must epoch launchers, I went from bugs that were where the actual runtime could tell me you did something bad here, to when I go to these must epoch launchers, the bugs start to become a little bit harder to even reproduce and spot. Right now, it takes me quite a while in order to really debug, because you're really taking the application correctness into your own hands. You're specifying things about your application. So at that point, you're not going to be as babied by the runtime as with the task launcher, which is great to start off with this end of the spectrum and then move your application slowly to the left. And then the last thing was just to highlighted what Wan Chan talked about earlier. A week into it, after trying to understand my application, I was told about using the Profiler and the Legion Spy applications, and I couldn't stress enough that I wish I had got this on day one. I went back, and it really revolutionized the way I thought about optimizing and not second guessing what was going on behind the scenes and profiling my application. So from day one, if you can really just start to learn the tools that that are given to you in order to perform profiling and inspecting the actual execution of your data, that's going to give you a lot of understanding of your application. One of the things I told Mike was I was doing a regular CG solve, and at one point I was looking at the way this was actually laid out in this example here, and it baffled me that it actually was not executing certain things in the order that I specified them. And so when I say things in this particular order in my file, and then I go to this example, Legion actually figured out how to reorder certain things in order to decouple the requirements of the regions that I was passing in. And I think that's when it actually sold home for me in order to say, hey, this is actually something that is, once I look at my application, this is what I said. Legion understood it without me having to go in and explicitly say such things. And then from that point forward, I was pretty much sold on the idea, and I could just jump in. So just from that perspective, if you're starting early and you want to get productive, hopefully if you have any questions about the specifics, I'm not an expert right now, but anybody that wants to talk about the numerical side of things, that's fair game as well. But if you're really trying to get into Legion development, I think looking at the source code, using the profiler and the other software tools, and just starting off simple and migrating to more complex code is the easiest way to get started in this kind of, in the Legion programming framework. So that's it. Any questions?
So I just wanted to talk about one particular effort that I, as part of the S3D user group, have been working on. So I'm wearing the hat of an application programmer here, and we started off where Sean and Mike left off, where they've actually done a full port of S3D into Legion. So in some sense, we are standing on the shoulders of giants. But we wanted to get familiar with the Legion port of S3D because we wanted it to be our short-term production version of the code. And we thought a good way to actually do that is by working hands-on with the code and doing something that's meaningful, which in this case was actually implementing realistic boundary conditions in Legion S3D. So some quick background on S3D. If you already don't know, you probably must have heard of it quite often. It's an explicit finite difference PDE solver for turbulent combustion. So the minute I say explicit finite difference, that should already imply a lot of things about the solver algorithm. A few other simplifications that S3D assumes. We only work with simple rectangular Cartesian fixed structured meshes. So that effectively means that the mesh or the grid is completely implicit. You don't do any work to set up the mesh, and you can almost set it up in a fully distributed parallel way. Also, we impose a perfectly load-balanced SPIMD decomposition. What that means is every SPIMD chunk has exactly the same number of grid points, has exactly the same number of fields it's working on, has exactly the same number of operations. But where S3D really tries to tackle the complexity is actually in terms of the physics that it's solving. So for turbulent combustion, it so turns out that S3D has a very large field space of the order of 100. That's just the primitive state variables itself. And this is about 100 state variables at each grid point. In the process of implementing the solver itself, the field space actually bloats up because you have a lot of intermediate fields that you need to generate, which are results of simple operations and so on. And the number of PDEs that S3D is solving is actually, it scales with the number of PDEs it's solving, and also the number of stencil operations that happen actually scales with the number of fields. And Sean alluded to that earlier. You have actually a lot of phase barriers in S3D, and that has to do with the number of stencil operations that are happening for each field. And as I said, The mesh that we deal with is actually very simple, but the focus is on implementing a rich mix of physics kernels. And the way S3D views it is basically it's a PDE solver, so the time derivative of every state variable is equal to some right-hand side. And the right-hand side is what encapsulates all the physics. So continuing, all of the right-hand side function evaluation port of the S3D into Legion was already done by Mike and Sean, and I must say they did a terrific job with very little involvement by us. That port also actually interoperates with the base S3D. The base S3D is just expressed in Fortran MPI. So they have decided to actually have the Legion port of S3D have it as a library that we can link to at compile time. The strategy that was used by Sean and Mike, and I'm sorry if I'm leaving anybody else out in the Legion port of S3D, but I want to credit everybody who was involved. So the strategy is manual spimdification. And I realized in the discussion that happened when Wanchan was giving his talk earlier that there were a lot of questions and understandably there are a lot of concerns on how this manual spimdification actually works. I had the benefit of seeing it implemented in Legion S3D. And I also wanted to mention that for some reason the Legion team was shy about saying that, but all of these concepts, what is must epoch, what is relaxed simultaneous coherence modes, what do phase barriers do, all of these are actually very nicely documented on the Legion website. I'd encourage anybody who wants to know more about it to go to the explicit ghost example on the Legion website. It's actually very, very nicely documented. So in this case, as is the case with any manual spimdification, you have a top-level task, which is a single task that actually sets up all the list of ghost regions that need to be exchanged between various SPIMD subdomains. And then the top-level task launches a bunch of what was earlier referred to as a control task. It so happens that in Legion S3D, they're calling it distribute task. But the distribute task is exactly the same as a control task that Wanchan mentioned. So each control task gets the list of ghost regions that it is writing to and it is reading from, and all the orchestration is done by phase barriers, which the top-level task sets up before the control task is launched and it's passed on. And essentially, the control task then launches all the physics kernels. So this is the same implementation in Legion S3D, and for somebody who's seen the code, I now see the rationale behind what manual spimdification is and how it works in practice. So I'm sort of a beneficiary of that. I should also mention that there was a lot of work done in other respects in actually getting the maximum performance out of S3D. And as I mentioned before, S3D has a lot of multi-physics kernels, and there was a lot of effort put into developing DSL compilers for chemistry and the transport kernels that gave a lot of performance boost on machines like Titan, where there's a host and an accelerator. And finally, as I mentioned before, the Legion port of S3D was implemented for fully periodic problems. And this was a nice natural starting point for the S3D group to take that code and then actually extend it to implement realistic BCs. So this is where my effort actually started. And I want to mention a few things that I learned about the runtime, some of the difficulties I faced, and some of the tools that I should have known were available for me to actually make things easier. So this is a typical scenario for physical boundaries. I mean, what you're looking at is basically the left bottom corner of a 2D mesh. In reality, the third dimension, you can just extrude this. Each block you're seeing is actually one chunk or SPIMD subdomain or tile or patch, call it whatever you will. It so happens that the boundary cells could be actually pertaining to different boundary types. So in this case, the left boundary, I'm calling it boundary type 1. I've colored it in red. And the bottom boundary is boundary type 2. So this is a common scenario in S3D. In fact, in S3D, we have about 7+ different types of boundary conditions. I say 7+ because we have 7 mature BCs, and there are some boundary conditions that are still being actively worked on. And my job, or our team's job, is to actually correctly implement all of them. One feature of the boundary conditions that we have in S3D is that all of these boundary condition tasks have very similar region requirements, meaning they read roughly the same set of fields from the same index subspaces and write to the same fields in the same index subspaces, except the math differs slightly or sometimes significantly between the various BC implementations. So knowing that, I had two options to actually implementing BCs in S3D. The first option that I was heavily leaning towards was actually implement and register tasks for each of the boundary condition type. This was partly inspired by how it was done in Mini-Aero, where for every different physical boundary condition type, you actually code up the task, have it registered, and then I was hoping, naively as it turned out, that I could have the right type of the BC task instantiated at runtime. And I'll tell you why I was naive about this. So in any given problem, you might not have all the, in fact, you will not have all the possible boundary conditions. So I was hoping that even by coding up all of those tasks, only the specific BC type tasks would get instantiated, but I'll tell you why that wasn't the case. The second option, of course, is actually have a generic boundary condition task, and within the task body, have branch statements that say, well, I'm on so-and-so boundary, and this is the boundary type as specified by the problem, so I'll do this particular bit of math. I wasn't particularly in favor of that, mainly because I didn't want to have branch statements inside my leaf task. That to me, for some reason, didn't seem like a very good idea. Okay, so as I said, I was leaning towards option A, where I wanted to register or code up all the boundary condition type tasks, have them registered. So, and the way I was hoping that the runtime would instantiate the specific type of task was actually using coloring and partitioning. So what I did was, for each SPIMD subdomain, I did a further partitioning of the index subspace into those that are interior. So in this case, all the white cells are interior cells, and the cells on the boundary would be pertaining to a specific boundary type. So as I said, we have 7 boundary conditions. So I would color all of the SPIMD subdomains accordingly. In reality, most of these colors would pertain to empty regions, because the problem would only specify 1 or 2 boundary condition types. But I would still impose that coloring and partitioning, and what I was hoping was that I would launch all the BC type tasks for all the SPIMD subdomains. But what I was hoping was, for instance, in the interior subdomain, there are actually no regions that pertain to a certain boundary type color. So what I was hoping was that the runtime would figure that out and say, hang on, there is no region requirement for the boundary condition task for this point, so I should not instantiate a task for this. So that's what I was hoping. And I said, yeah, as I mentioned, if there's a boundary condition type, even on the boundary that does not exist, that amounts to a no region requirement, and so that task shouldn't be instantiated. But turns out that did not happen. What was happening was that every boundary condition type task that I registered was getting instantiated, even if there was no region pertaining to that BC type. And this prompted a discussion between Mike, me, and Sean, and I was asking them, well, I'd assume naively that if there is an index-based task which has region requirements, all of which amount to no regions, why should the task ever be instantiated? And then Mike had a very good reply to that. He said, well, you could actually have instances where a task does not have any regions, but it might still be getting some arguments, and it might want to do something with them. So the runtime is erring on the side of safety here, and it's saying, I'm not going to make any assumptions about what my region requirements amount to in practice. I'm still going to instantiate the task, which sort of brought you could call it a philosophical question, but the question that I had was, if you have an index launcher and an index-based task with a certain set of input arguments and a certain set of region requirements, but if it turns out that all the region requirements are null or no region, conceptually, what is the difference? So in my head, there's a clear pecking order as to what should dictate the instantiation of a task. To me, and this is completely from my biased view of S3D, is that the region requirements followed by futures followed by arguments should influence a task instantiation. I'm sure there's a good reason why that should not be the case. I also had another question, and again, it's something to ponder about for application users as well as Legion developers. What if I had a task that had all the region requirements as read-only? To me, in my head, that's a dummy task. I mean, if you're only reading inputs, not doing anything with them, not writing to any region, then you're technically in no critical path, or it doesn't matter if you run or you don't run. So why should the task be instantiated at all? Again, it's something to ponder about. So these were some of the observations that I ran into, or I had in the process of porting BCs. Some other miscellaneous observations, and I don't mean these in any way as criticisms, but one thing I realized was, in my case, I was running into a scenario where I passed a no region requirement, and I was blindly iterating over the index space or the domain within that task, and I had all sorts of crazy runtime errors, and I couldn't figure out, and it took me a couple of days. And because all of it was because my starting assumption was wrong. I now realize that there are actually simple tools. The debounce check compile flag would actually save me a lot of time there, and there are other functions that let me query whether a region actually is physically of any size or if it's null. Another thing that I found was that the concept of projection functions is very useful, especially when you want to implement boundary conditions. It's a very powerful concept, but I find that there's very little documentation of it in the Legion website. I actually found some discussion on a thread on the user forum, but I find that, I mean, it's a powerful concept, and it's a shame if there isn't an example of it on the Legion website. Another thing that I find is that in S3D, boundary conditions require some specialized stencils. We might need actually in-plane derivatives. As of this morning, that was slightly tricky for me, or at least in my head. But then with the concepts of doing operations on intersection or intersecting, or doing operations on logical regions that have intersections or unions, that actually would solve my problem quite a bit here. So the third point is actually slightly outdated. And then, yeah, the last point, I really want to echo the last speaker. It really was very, very helpful just popping the hood and looking under the hood. So opening the legion.h or runtime.h files and looking at all the functions that are already implemented was super useful. And again, I want to commend the Legion team for that. So with that, yeah, that's all I have.
Any questions? I'll give a quick answer to one or two of them.
Sure.
Right. So there are other ways to have side effects in Legion. And to one of the questions earlier, currently the model is we don't do any dead code elimination.
Sorry?
We don't do any dead code elimination. So if a task is useless right now, the thinking is the best we would do is warn you that you've launched a useless task, and you need to decide whether you really meant to launch it or not, because some side effects that we can see there's no side effects within the Legion data model, but you may be touching an external file or doing some other stuff that we can't see. So we're fairly conservative about eliminating things that look dead to us right now. That said, I think we're going to add a flag for other reasons where you assert that there are no side effects other than what's in the Legion data model. And once we have that flag, then maybe we can be a little bit more aggressive about throwing stuff out.
So, I mean, I just had a side comment on that. I think it's very interesting to see that I think often runtime developers and programming models developers don't give applications developers enough credit. They often think that it's going to be too hard for them to think in terms of inputs and outputs and think about everything that has to come in and everything that has to come out. And you've actually gone so far that you've gone the other way, and you've said, I've thought about all of these inputs and outputs, and if it's all inputs, it shouldn't do anything. Which you're right, conceptually speaking. But we've been so conservative with our programming models that we're saying, well, they're just going to want to think about it like a computer, and it's going to just do what it does, and they just specify minimum. And that's, I think, where the dissonance is coming. So I thought that was interesting.
Thank you. Can you hear me? All right. So this is Philippe Pibet, and well, I guess I have -6 minutes to do my talk. So I'm going to try to be quick. Let's see. So this is joint work with Janine Bennett at Sandia. Unfortunately, Janine is not here today. She's sick. And so this is joint work, but also with special thanks to the Legion team, whom I have bothered a lot over the past few weeks. So I want to say that this, what I'm going to present is a short abstract. It's a short presentation of a bigger piece of work, which is actually contained in this SAND report for some of you who are interested. And I just posted it in the Legion users discussion board this morning. So if you want, you can upload the full report there. All right. So why are we doing this? So at Sandia, we wanted to design, develop, and evaluate a unified data-driven approach for programming applications and in situ analysis and visualization. So what that means is that this was mostly a proof of concept effort to move from a bulk synchronous MPI type of approach for in situ analysis, which we already have, to an AMT approach. So this is exploratory work, and in particular, what was of interest to us was to study the interplay between data-centric programming model requirements and how this would play out in in particular in the context of extreme scale codes. And we wanted to assess the impact of these requirements on the design and the capabilities for both applications and supporting in situ infrastructure. So this is why we did this work. So what did we actually do? So, and that's what I'm going to present today. So I'm going to describe our first effort at using Legion, in particular to support data-centric in situ data analysis, and how this provides foundation for a more efficient workflow handling. And in particular here, we are reporting on the proof of concept implementation. I'm not going to give code snippets in this presentation. They are in the SAND report. And also, I'm going to report on the current challenges which we're discussing, some of which are resolved, some of which are not completely resolved. All right, so in order to do this in situ analysis work, we needed to have a main driver, a main scientific application. So we used the mini arrow, the Legion version of the mini arrow that was presented before by Wanchan. We have plans actually to do this with S3D, which was just described by Hemant. So I'm not going to spend time discussing the mini arrow, other than the fact that we're using it as a surrogate, right, for real scientific code. For the purpose of our study, it's just sufficient. But I'm going to say a little bit more about what kind of analysis we're interested in. And so we're interested in porting our data analysis tool sets, which we've developed over the years, a number of years ago, and over the years together, Janine and I, and with a few others, which is part of the visualization toolkit. So it's a set of C++ classes which are part of this Titan informatics toolkit, itself a part of the visualization toolkit. And with parallel implementation using SPMD model with MPI. And well, the general workflow is the following. So basically, we've decomposed a typical data analysis workflow into 4 operations. Those 4 operations can be done, all of them can be done as part of an analysis workflow, or just some of them, depending on the nature of the work to be performed. But the general idea is that given data, right, and possibly given a previous model, which might not exist, but so this is knowledge and this is observations, we may learn a statistical or a data model, a model on the data, from which, and the primary model, and from which we can derive additional quantities. And given a statistical model, then we may want to assess data with respect to this model, for example, to pick outliers, right? And there is another operation, which is kind of we don't do this very often, but the test procedure is akin to statistical hypothesis testing. This is the whole idea to see how a given model fits with some data. So basically this workflow, we designed this workflow a number of years ago because it mimics what typical data analysis patterns do. What's also interesting is that in terms of writing parallel applications, this paradigm fits very well parallel implementation, at least in the SPMD world, because the only operation that requires explicit inter-process communication is the learn phase, where from a number of distributed observations, you're going to build a global model. All the other tasks are inherently embarrassingly parallel because they can all be process local. And as a result, the tool set which we've developed using MPI, we thought is a very good candidate for this this research work with Legion, is because we know this is kind of the baseline. We know that with the SPMD implementation, we have something that works and that scales optimally with up to almost 1 million processors. I mean, actually, the largest test we did was like, it was the order of 200,000 cores. And so I'm just going to say in the SPMD world, so basically we're going to set aside the operations that do not require inter-process communication. We're just going to look at one very simple example, which is the case where you want to compute, say, a histogram. Right? So you have data that are distributed, you have a distributed data set. In that case, say it's distributed across 3 processes, and you want to compute a global histogram, right? So the learn phase, what it would do in parallel is that it would first compute local histograms, right? And then you would have effectively something which is a map-reduce operation, right? Where you need to union all the keys of your histograms, sum the keys for each values, and then you'd have to broadcast the results so every process has the statistical model, the same one for further data analysis. And this is one type of data analysis, which involves a map-reduce operation, which is an all-gather, compute, and broadcast. Right? There is another model, which I'm not presenting here, for moment-based statistics, where instead, because you will have a very small number of keys, rather than doing this reduce operation on just one or a few nodes, you can actually do a global reduction. But the bottom line is that in the SPMD implementation, there is only one step that requires explicit communication, and this is what in the end we have to translate into the AMT world. So here's what we did. So using the concepts of Legion, retaining, that was the main constraint. We want to retain the learn, derive, and assess workflow because we know it works for data analysis. So we wanted to retain that. That was a strong constraint. And instead of thinking in terms of inter-process communication, now we have to think in terms of asynchronous many tasks running at, well, we don't want to have an explicit barrier, effectively, right? So instead what we did is that we used, and so we're replacing the inter-process communication with what you see here in red. I mean, those red rectangles represent logical regions, right? So basically, the top-level task creates what I call an aggregation region, which is a region which effectively will serve as a surrogate for MPI collectives. And because those operations that we have to do are commutative, right? The order in which they are performed doesn't matter. All we want is completeness, right? We want to obtain a correct result. We want that all tasks complete, but the order in which they complete doesn't matter, right? They can all contribute, if you want, in the order that they want. And so Legion seems to provide exactly the right abstractions to do this, right? And so instead of thinking in terms of exchanging data, now we just have to think in terms of set operations. So in a way, the mapping from our SPMD implementation into this AMT approach was just a matter of rephrasing exchanging data with just set operations. And this is what we did. So So I rewrote a few of the existing statistical engines. I rewrote them, the parallel statistical engines, I rewrote them in, well, using Legion. So I rewrote a small toolkit, effectively, which now had to be interfaced with our proxy application. And this is where we would like something more portable than what we have today, because today, the footprint on the application code is small, but yet not negligible, right? What that means is that the Legion version of the mini arrow code requires to be modified substantially. It's about 80 lines of code, which I think is too much, right? So there are a number of files that need to be modified, and that we modified. So basically, in order to do this in situ analysis, it's a little bit invasive inside the main code, right? And in particular, and that's something that has to do with the way the Legion mapper is written, is that in order to do this, you need the main code, the application code, needs to know a lot of what the analysis code is going to do. It needs to do its internals so the mapper can be modified accordingly, right? And in terms of portability, that's not good, right? So the API should be, well, there are some improvements to the Legion API that should be done to resolve this. So I just want to see, I mean, we have much more results, but this is a very simple thing which I just wanted to report, is that basically we've done a number of tests, but the first one we would want is to make sure that the computations are actually correct, right? So we were able to verify that when we divide the same piece of work in an arbitrary number of tasks, well, there are some limitations to the code. It has to be a power of 2. But that when we do this, we actually find the good results. So in terms of algorithm correctness, things work. I mean, conceptually, what we've done does work. In fact, in most cases, we even find results that are closer to the truth than what, for example, Octave would find. With some caveats, though, because we've made some of, I'm not reporting this here, but last week we realized that we have some problems in terms of consistency. Sometimes it seems that we have some race conditions on these distributed regions, right? We don't know yet why. Maybe we'll discuss this tomorrow. Okay, so something I'm just reporting, it's a very simple scaling plot. The reason why I'm giving this one is to show that we don't have optimal scalability, right? So even with this is strong and weak scaling. So even going from 1 to 2 cores, I mean, clearly it's a log-log plot, right? So we should have a straight line, and evidently it's not optimal. And we've tried this. I've extended this to 128 tasks on 128 cores for both strong and weak scaling, and they are really scaling performance issues at this point. So this is another thing we need to address. But the main findings is that I think in terms of proof of concept, I was happy. I mean, I'm very happy to have done this work with Legion. I really like the abstraction that it provides. It seems to be a valid approach for in situ analysis. I have great expectation that this will work, but there are things to be addressed, right? So one of them was the problem is that sometimes, even though we're using exclusive read-write permissions on some regions, well, things don't seem to happen the way they should. We also have scaling issues and some Legion API improvements that we could suggest, and this is something maybe we'll discuss offline tomorrow. And with this, I am done in less than 10 minutes.
Do you think the concept of aggregation regions is a strong concept for doing collectives, and is that something that's going to percolate into the runtime, or what is the Legion strategy for collectives in general?
Yep, this is. Yes, you mean this, right? The fact of using a region as a surrogate for a collective operation. Yes, I mean, in fact, until you spoke about it earlier today, I was trying to think in the following way, which was, okay, if we're going to use AMT programming model, I mean, let's do it in that way, like in a completely asynchronous way. So I was not trying to do SPMD Legion, as was discussed earlier by Won-Chan in particular. And I was thinking, we're not doing MPI, so let's not do SPMD at all, right? Let's just try to think in a completely asynchronous way, right? So I did not explore at all this dimension. I mean, and in fact, to me, that's, I don't know, we have to discuss this, but it seems a little bit odd, right? I mean, if I'm going to use a data-centric programming model, why would I try to do SPMD, right? I quite don't get it, but maybe we can discuss this tomorrow.
So I'd say the quick answer is we don't actually have an answer that we think is definitely the right answer yet. There's a couple different ways to collect data. The aggregation region is one. Tasks can return values, and we can do a reduction on the future. We can also just literally do reductions into a single element of a region. And I think we've tried all of those in different cases and found pros and cons with all of them, but not to the point where we're ready to pick one and go. And it may actually be that the answer is that there isn't one right answer, that you need to be able to choose the right thing for, you know, how big is the thing you're reducing, you know.
Yeah, well, that's the thing. How big is the thing you're reducing? And I think that's the key thing here.
So,
Yep.
so the more and more we're hoping that, you know, there may not be one right answer, but there may be 2 or 3 reasonable answers, and more we're hoping that these things start existing as abstractions that people build and can put on top of either the C++ API or on top of the Regent language, so that not everybody has to roll their own, right? If you want the aggregation region-based one, there ought to be a library to do that. If you want a global, a single value that you do reductions into, there ought to be a library to do that.